Hello everyone, welcome to lecture number 17. Today's lecture is going to go through a design exercise with Twitter as an example. At this point, we've seen end-to-end a lot of different techniques for building scalable architectures. We have, I think, a pretty complete end-to-end view of how to build a scalable architecture for services. On the front end, I just want to review that now so you have a single reference point for this. On the front end, we have load balancers that can handle a lot of requests, either because they're doing very little work or they're using DNS to globally distribute the connection point of requests to different servers around the world or in a single data center. Those load balancers can hand off, don't actually do the work of servicing the requests, but just hand them off. They're proxies. They hand off the requests to the service layer, which is have thousands of clones of the same application running on different machines. If the application is stateless, that's very easy because they're all interchangeable. All the different clones are interchangeable. They all would give the same result. We'll talk later on about how the operating system in VM can be abstracted away to develop using containers or serverless functions. We haven't quite gotten to that yet. That's kind of a minor point. At the storage layer, there's been quite a lot of discussion about different strategies to make that scalable, because that can certainly become a bottleneck. That's where we need to coordinate all the things happening in the big system. NoSQL databases are a good way to get scalability because they're implemented using a hash-based partitioning scheme called a distributed hash table, which means that requests coming in can, again, not go to a central bottleneck, but go immediately to the appropriate partition. SQL databases have some advantages in terms of the lack of duplication and consistency and the ability to support transactions. And you can scale them to some degree using read replicas for the reads, or if you need to scale the writes, you can do sharding, although that can be a challenge to implement well. All right, so I'm going to go through an example with Twitter. This actually comes from the book by Kleppman on data-intensive applications, the O'Reilly book. With the borer on the cover. And in this example, I think this actually does reflect the real history of Twitter, Twitter's design, but it is somewhat simplified to get one main point across about how to deal with storage of tweets. Okay. So in the first design, we imagine that there is a SQL database used. Okay, this is the simplest design. This, in fact, was how it was originally designed. So we have users. Okay, here's the user table. So the user number 12 is Jack. Every user has lots of followers, so because there's a many-to-one relationship, we have to have a separate table for those followers. And here's an example of a follower who's following Jack, right? And then when Jack tweets, his tweets are added to this tweet table, like this. Again, there's also a many-to-one relationship here. Every user has lots of tweets, right? So you need to have tweets in a separate table than users. And by joining together these three tables, we can build a feed. So, for example, if you are the user number 17 million here, right? Whatever this number is, you want to see your feed. What that means is you want to see all the tweets from people who you follow, and you want to have them sorted chronologically. So you have the most recent at the top, right? So in this table here, the follows table, you can find all the rows where you're the follower, and that lists some person you're following, which we're calling a followee. Okay, so you take all those rows, and you join these to the user table based on an ID, so that you can get the actual name of the person. You can translate this 12, for example, into the name Jack, because that's going to be rendered on the page. You're not going to render the number 12. You're going to render the Twitter handle, and then you join a list of all those lists of followees with the tweets table to filter out. Basically, we filter the tweet table for all the tweets from those users whom we happen to be following. So it's like a three-step process. So really, there are two big steps here. First, we look in the follows table to find all the people we're following. So there's some set of rows that list out for this particular user. So we filter on this first column, basically, right? And get all the rows and for all those rows, we are using the second column, and for that set, we filter this tweets table using that set of values, all the followees. Okay. And that works. Now, the problem, though, is essentially that it makes reads easy, but makes reads difficult and writes easy. Whereas in reality, reads are more common than writes. So in other words, building a feed is something that happens all the time. People that go on and check their browse the app. That should be fast, whereas this design makes that slow and is optimized for making the tweets fast. You do a lot more reading than tweeting, and most people do. Maybe celebrities don't. So it's kind of building out the feeds is kind of slow, right? So notice that I say writes are fast because if you tweet, all you have to do is make a new row in this tweet table that has your sender ID, has like your Twitter handle ID here, the text of your tweet, and then the timestamp of when it was made. Notice, just as a side note, when you see timestamps in databases and in software applications, you often will see them represented with a long number like this, which is epoch time. It's the number of seconds elapsed since 1970, January 1st in London, Greenwich time. Okay, that's just a convenient way to represent time as an integer. Now, so adding a tweet is easy. You just write it in one place. But getting your feed is slow because you have to check multiple tables and do a join. So I say it's slow. I want you to stop and think, though, about why it's slow. What about it makes it slow? There are actually several things about reading, about building your feed that make it slower than it needs to be, right? So I guess to put it another way, how can you think of ways to make this faster? Or can you think of see reasons why it's slow? And so to help you figure that out, I'm showing you an example of what the tweets table looks like, just to make it a little more obvious. So here are a bunch of tweets, right? So the ID here just refers to like the tweet ID. That's not really important. The more important thing is the sender ID, right? So first we have, let's say Jack tweeted here, and then again here, and then next time Jack tweets is down here, and so on. And here are a bunch of other users who are tweeting, right? And they have their tweets listed in time. You might imagine maybe these are sorted. If you keep adding just to the bottom, you can imagine in storage they're kind of like arranged in that manner where the latest tweet is on the bottom, the oldest one is on the top, and that's kind of like maybe linearly arranged in storage. So what about this would be slow to build your feed? Now, to answer that question, I want you to stop and think about it. But what you should have, one of the things that's important is that you're following lots of different people, and their tweets are scattered throughout this database, right? So that's the big thing. The second bullet point here is, I think, the most important thing. When I'm reading all the tweets of people I follow, they're not in one place. They're not like together spatially. They're distributed throughout the whole table, right? Because people are tweeting at there are lots of different users, and I'm not following everyone. If I was following everyone, and I just wanted to get the most recent tweets, I would just look at the bottom of the list and pick out that chunk. So it'll be one block of data that's like contiguous. Contiguous blocks of data are much faster to read, either from disk or from memory. Both of those storage systems are optimized for doing big writes. If you're doing a big write, you can do it in parallel and stream the data at once. Remember, also, if you think about a disk, it spins around and has a read head, sort of like a record player. It can read from one location. To read from neighboring locations, it just waits and lets the disk spin, and that allows the read head to move over a range of values, right? But also, solid-state disks and memory have the same kind of optimization, where reading just one little tiny piece of data is just as fast as reading a large block of data in the same location. Right? If you're going to read one little bit, you might as well read like a whole big chunk. I mean, there's a limit. Once you get to a certain size, it starts to get slower. But if you're reading a lot of little things scattered all over the place, that's really inefficient. So that's one big problem with this design. Another problem is that I'm reading from 3 different tables. I have to check the follows table, the tweets table, and the users table. And notice that both the follows table and the tweets table have this scattering of data, right? Because I'm going to follow people over time, like not all at once. So the records of who I'm following are going to be distributed throughout that table. And that scattering of data is also a problem if you are sharding the database. because then the tweets from all the different users might be in different shards, so you have to contact multiple machines. But the key thing is, even if that's not the case, even if you can fit this all in one database, it still is pretty inefficient for reading a feed because of that scattering of data. And there's no way to fix this scattering. Also, this comes back to the sharding issue. We'll talk a little bit more about this, why sharding a social network is difficult. There's no way for you to go back and retroactively try to rearrange the data so that it works for everyone, because every user is following kind of a random subset of different users. There's no one place to put someone's tweet that would work well, efficiently for all the different people who are following that person, because you would be putting it next to someone else's tweets, and it's not clear that other people would be following. You can't find like the one perfect person that everyone else is following. If someone follows you, they don't necessarily you don't have too much information about who else they're following. I mean, there's a little bit of correlation, but it's not perfect. Okay, so hopefully that motivates the idea that hopefully I've convinced you that reading tweets from a normalized design in a SQL database is kind of inefficient. So the solution to this that Twitter came up with, and that I'm going to talk about, is to pre-build your feeds. In other words, to denormalize the data. Whenever someone tweets, so here I'm showing the user posting a tweet, instead of just storing that in one place, you actually replicate it and store it in a special place in a feed database for each user. So if I have 3 followers, there are going to be 3 copies of my tweet now. That ends up being, so that space-wise is much less efficient than the original design. And work-wise, it's also a lot less efficient. When you tweet now, you have to not just write it to one place, but write it to all your followers' feeds. And if you're a celebrity, you might have millions of followers, right? So that tweet's gonna cause a million different writes, or millions, right? We're gonna come back to that problem. But that's the design. Now, the benefit of this, of course, is that if a user comes in, now this diagram is like a simplified view of what's happening with the data. I'll have another couple diagrams later to make it more concrete of how this is working. But just at a high level, when a user comes in and checks their timeline, their feed, they make an API call. If there's a place in the database where where my feed already has been built, in other words, I already have a list of all those tweets from my followees, the people I'm following, and they're in the right order, I can just read from there. It's all in one place. Now, it's true that some of those are going to be duplicated. So this tweet number 5 is in 3 different places, 3 different feeds from different users. Each of those users, when they come in, can read quickly their feed. That's the benefit of this design. But the downside, like I said, is that the posting of tweets is slower because there's a duplication of the data that has to happen. And also there's an inefficiency in the storage because there's duplication of the tweets, right? So one of the things to think about here is, do we really want to make tweeting slow for people who have lots of followers, like they have 10 million followers? Probably those are the users that are the most important in your system, so you don't want to do that. So let's think about those celebrity tweets, though, how to deal with them. All right, so here's the phone for the celebrity, right? The app makes a post request, let's say, in response to them typing out a tweet. That goes to the Twitter backend. The Twitter backend has to do like 10 million different database writes. And those are all in different locations too. So there's 10 million, like, it's not just a lot of data, but it's like a lot of separate operations involving round trips to the database. So that's like really slow. That operation has to finish before the tweet is truly published, right? So in a simple design, the backend accepts the request. It goes through like a loop, or maybe it can parallelize it on multiple threads or across multiple machines. But anyway, it has to do a lot of work in the database, and when it's done, it can give a 200 OK. Okay. Now with this design, the simple design, celebrities' tweets are going to take a long time. They're going to hit tweet, and they're going to wait for like maybe a minute before it finishes. Okay, that's not a good thing. So what would you do to fix this problem? Well, if you remember last lecture, we can defer the work. We can do it asynchronously. So this connects very closely to last lecture, and that's why in the last lecture I actually was peeking ahead and using Twitter as an example. These two lectures really go together. So when we do these writes asynchronously, we can have the backend give a 200 OK response immediately, and put a message on a queue to cause all this work to happen later. That's one solution. And a second solution that we're going to come to at the end of the lecture is actually to store the celebrity tweets differently than everyone else's tweets. So maybe for a typical user that has like maybe 100 followers or something like that, it might be okay to do it synchronously to make all those updates. But then maybe for the celebrities, have a different way of storing their tweets. Okay, so we'll come back to that later. The first solution is to use a queue. Now, once we use this new architecture where we have a feed database that is pre-built and stores all the feeds for the users, we're going to make that a NoSQL database, and that's going to be updated later after, it's going to be triggered. That update is going to be triggered by a message in a queue. So we have a front end that gives a response pretty quickly. After all it has to do is authenticate the request to make sure that it was the user has permission to tweet. It puts a message on a queue, and that's handled by the publication service. The publication service might have to do a lot of work to update a lot of feeds, and then later on I'm decoupling that from a notification that happens later as well. Okay, so I'll go through this in a few slides to give you more detail about what's happening here and to reinforce the benefits of queues and how they fit into this design. But yeah, this is what it looks like at a high level. I'm going to call this Twitter 2.0. And we no longer have a relational database to store the tweets. This account database might be relational and followers might be relational, but instead we have a NoSQL database to store the feeds. This can be scalable. Now remember, we're storing a lot of data here because we have a lot of duplication of all the tweets. So it becomes even more important to make this scalable. We'll see that a NoSQL database works well for this design because there's no need for references. All we need is like a key for the user, and the value is the feed. Okay. So writes are still fast in a sense, but they're only fast because we're deferring the work and doing it in the background. So, it does actually still take a long time for the write to have full effect, but that work is happening in the background in response to reading the work off of the queue here. And we do that asynchronously, okay? Yeah. So to get your feed then, let's see why this is fast. This is the common case, of course, just the user browsing the app. The mobile app makes a GET request to a certain API endpoint to get the data. This API service, this API gateway we might call it, checks the authentication token is valid. That's step number one. It might have to make a call to this microservice on the side to do that, or it might have a cached response from a previous request that it got. And then at that point, it does a query to this NoSQL database, this feed database, to read the feed. Okay, it uses the user ID as the key. It got the user ID by translating the session key. The authentication service basically gave the user ID after checking the session key. And notice that when it makes this request, although this might be a big NoSQL database with hundreds of nodes even, all of the data for that user is going to be on a small number of replicas because it's just one row in the database. In each row, the key is hashed to tell you which of the nodes the data is stored in, or which subset of the nodes. So you can actually make a request to just one node here to fetch the data. All that data is going to be located contiguously in storage, hopefully. I guess that's a detail that might vary depending on the database and how you update it. But if it's truly just a key and a value, then it should be in one place. So this is that's fast, and this is a scalable design. So we get back maybe a JSON object from here, and we return that JSON object back to the client. Now, just as a reminder, the reason why these NoSQL databases are scalable is because this hashing to find the node happens at the client side. So it's a shared nothing system with no significant central bottleneck for coordination. The servers don't need to coordinate much with each other, at least not for the individual requests. Only time servers need to coordinate with each other is when the number of nodes changes or nodes replaced. Every request involves a constant number of servers. So the picture I have here is meant to illustrate a real world system that is scalable in the same way, which is to say these ticket booths at the state fair. Okay, so if you want to handle more users selling tickets, you just add more booths. And when the users show up, they will kind of like on their own, without asking any one person, they'll assign themselves to a line to one of these ticket booths, and they'll wait. And these ticket booths can operate independently in parallel because selling tickets doesn't require coordination. If someone asks for a ticket and they give money, it doesn't matter what's happening in any other booth. The decisions that the seller makes about handling that transaction are entirely dependent on just what the client asks for, that one client that visits the ticket booth. It doesn't matter what's happening in other ticket booths. I mean, that you could make this more complex, and then this would become less scalable. So, for example, if there was a limited number of tickets available in the fair, then there would have to be some coordination to make sure that you didn't oversell the things. And it would be, you can make this even worse by saying you had a lot of different types of tickets, and each one had a different limit of number that could be sold in a day. That would make it less scalable because there would have to be some coordination between the booths, right? But if we're thinking about a simple NoSQL database or a simple ticket sale operation, there's no coordination needed between the nodes, between the workers to handle more load. All right, so it's kind of perfect scalability. Okay, just want to review that and to make that clear. When we look at the Twitter feeds in a NoSQL database, we want to store that using a simple key value abstraction. And fortunately, there's an easy way to do that. We just use the user as a key. Here I'm showing the user names, but more likely it would be like the user ID, like a number that corresponds to the user. And the value is the feed data. And maybe it's just the latest feed data, because you don't need to, the user is not going to very often browse to the 10 years ago in their feed or something like that. They just want to see the stuff at the top. So you store that here, maybe in a JSON object, or maybe in a dictionary, or a wide column in Cassandra, if that's what you're using. This example kind of shows what it would look like in Mongo. So we hash the key to figure out which of the replicas we will find this particular row. Notice this view that I've drawn here is an abstract view of the dictionary of all the storage. In reality, the rows are distributed across a lot of nodes that are handling the data. And of course, there's replication, so each key hashes to a set of nodes, maybe 3. Okay. I said before already that data is duplicated, so a given tweet is going to appear in multiple feeds. We call that denormalization. But the benefit is that finding the data for a particular user is fast. It's already pre-built. It's in one location. It can be efficiently read. And it's, in one node also. One machine is involved in each request. So you can add more machines to handle more load. By contrast, in the original design with a relational database, we had 3 different tables, right? Users, follows, and tweets. And in order to build a feed, we had to join these. So we took our user, we get our user ID. We use that user ID to find all the people I'm following. I've simplified this to organize them together, but in reality, these would be scattered throughout the database. So then I take the set of followees, 10, 3, and 325. I have to use those as a filter in the tweets table to get all the rows that match those users, right? So for example, my feed is going to include all the tweets from user number 3, also all the tweets from user number 10, user number 325, and those are going to be scattered throughout here, right? Now, I've mentioned that the scattering is a challenge for for reading compared to reading from one place. Also, if the system gets big, we're not going to be able to store the tweets in one place, either because the storage isn't big enough in one machine, or more importantly, the volume of writes that are adding new rows is so high that it can't be handled by one machine. That's probably the more important reason why you need to scale this out. So you could still have a relational database, try to make this work. Even if you don't care that the feeds maybe are a little slower than getting the feeds is slower than writing new tweets. For a certain amount of time, this might be okay. The first step to scaling this is to do some sharding, to partition the data, especially the tweets data, because the tweets data is the big data. Partition these tweets into different machines to store the tweets. I mean, follows also might be a big table you need to partition. We're going to see that presents a problem for tweets, though, for this particular design. We don't have an easy way to partition. We can partition. What I mean by partitioning is we have to have some rules to figure out where to store the rows. Remember, every partition is going to have all of the tables, but every partition will have a subset of the rows. Let's assume for now we don't need to worry about users and follows. Maybe these are small enough that we can even duplicate these on all the different partitions for efficiency. But tweets is the biggest table. We need to split that one up. The obvious rule for that maybe is to partition based on the user ID, right? Because we know that if someone is reading tweets from user 3, they very likely want to see all the tweets from user 3 because they're following that person. So you do want those to be in the same partition. So if you could use a hash-based partitioning on the user ID, that assigns a partition to these tweets. But if we want a query to be efficient, we want all the tweets we're reading to be in the same partition. Okay. We want all of our followers to have quick access to our tweets when they're doing the read with this relational design. Okay. Now remember, I've gone back to Twitter 1.0, so keep that in mind. I'm going back and reviewing one of the challenges in that original design, and in particular looking at the partitioning of the data with a sharded design. Okay. Problem is we can't. Fundamentally, it's difficult. It's impossible to assign partitions to users in a way that'll make all the followers happy, because the relationships between people in the real world and on Twitter and on other social networks is a semi-random graph. A random graph is a graph where where the edges are assigned randomly between nodes, right? And this is an example of one. The graph we're talking about is the social network, right? So the nodes, these red nodes represent people, and the black edges represent like following relationships. Although I guess they should have arrows; they should be directed. But just assume that all the relationships are bidirectional, which is not true for Twitter. It is true for Facebook, for friendships, and it's also true for LinkedIn, but not true for Twitter. But anyway, because of this like random assignment of who is following you, based on the random interactions you have with people in the world. If I need to assign this node, because this node here is connected to so many other people, there's no way for me to assign it to one partition such that all of its neighbors are in the same partition. Because if we follow that through, the only way to make that work is to assign everyone to the same partition. Now, if this was more structured, we would be able to partition it with very few crossings, very few cases when users in one partition were related to users in another partition, but that doesn't really reflect what a social network looks like. Okay, so this is a review of what I talked about in the data partitioning lecture for scaling SQL databases, but that's an important concept that I want to make very clear. Okay, so we can't cleanly partition the default followers data, and that also means that we can't partition the tweets in a way that we would not need to check essentially all of the partitions when we're reading our feed. And if we're checking all the partitions when reading our feed, then we are not getting any throughput benefit by adding more nodes, and so we don't have scaling. In other words, every node is involved in every single read, and so you need to have nodes that are fast enough to handle all of the requests in the system, and that's not a scalable design, because your requests are going to keep getting the number of requests keeps going up when you scale, yet the capacity of a single machine is bounded. There's an upper limit at any given point in time to how fast a machine is. Okay, so we had a trade-off here, actually. There were some, in the relational design, there were some good things. So first of all, writes were simple and fast. We just had to add a row in one place. We also, another benefit here was that the amount of storage was minimized. It was a normalized design, so we only wrote to one place. There was no duplication. The downside, though, of the relational design was that once we made the system bigger, when it scaled, we had problems because we couldn't handle a lot of data or users. Because once we have a lot of data and a lot of requests, we need to have more than one database. We need to partition the writes, and doing that is difficult with a social network. We also had reads that were slower than writes, which was a problem because reads are more common. The solution was to pre-build the feeds. This allowed us to use a NoSQL database, which is much more scalable, to involve just a subset of nodes, let's say 3 nodes in every read of the tweets. Now, the problem, though, is that there are 2 of them. First of all, we have wasteful use of storage. So every tweet is duplicated in every follower's feed. And for celebrities, it's even more wasteful. So if you have like 1 million followers, your tweet takes up 1 million times more storage than what it needs to. There also is a lot of slowness here in the write. So instead of just writing the tweet to one place, so we're paying not just for the storage, but also like there's the cost of the time it takes to create the storage, to write the data, right? Especially for celebrities that have a lot of followers. There's going to be a lot of writes, and they might not, those tweets might not reach all the users' feeds within 5 seconds. Even if we introduce asynchronicity to make the celebrity's user experience good, the celebrity might tweet and it looks fast, and they see the tweet in their own feed maybe, because the UI locally can do that. It might still take like a minute before some of the followers see that tweet because there's so many writes happening. And that's not a good thing in terms of like what Twitter wants the experience to be for celebrities. They want it to be able to support like conversations. If two celebrities are following each other, they want those people to be able to like send tweets back and forth, almost like a chat interaction, right? Like within seconds, they want those to appear. There's also a lot of work to do that publication, that duplication of the tweets for all the followers. Okay, so I want you to think about how Twitter can better manage this trade-off. So design 1.0 was good for writes but bad for reads and wasn't scalable. Design 2 was scalable. I mean, there was a cost you paid for it in terms of duplication, but that's okay. The big problem, though, is that celebrities are getting a bad experience. When a celebrity tweets, it takes a really long time for it to reach all the followers. So essentially what I'm asking is, how can Twitter retain the benefits, the scaling benefits of pre-building feeds while allowing celebrities to get quick reactions to have their tweets go out fast? What do you think? How can you combine the best of both of these? It's kind of a little nuanced thing that's pretty clever. Well, I hope you paused and thought about that. The solution is a hybrid design to actually use both at the same time. The key thing is that the downsides for the scalable design, that NoSQL design, that pre-built feeds, the downside really only existed for celebrities. For everyone else, it was okay. Like when I tweet and I have let's say I have 100 followers, which I don't even think I do because I don't use Twitter. That's pretty fast for me. I don't have to worry about a delay there. And most of the users are in that category, and most of the writes, most of the tweets are tweets that very few people are going to read, right? So the problem really only exists for these celebrities. The key thing to notice is that there are only a few celebrities, right? Like there might only be a few thousand celebrities that really have a ton of followers, or maybe 10,000. But anyway, it's a small number. It's a small enough number, in fact, that you could fit all of those tweets and you can handle all of those writes on one machine using a relational database. So actually, the original design works really well for celebrities to handle for both the reads and writes of celebrity data. The new design works well for everyone else, for people without a lot of followers. And you can use them, but there's nothing to say that you can't use them together at the same time. And that's what Twitter actually does. The simplified version of Twitter, which I'm calling Twitter 3.0, will do both. So if you don't have a lot of followers, your tweets will go straight to the NoSQL database. So you have pre-built feeds for most users. When I look at my feed is actually going to be stored in two places. So there's going to be a pre-built feed for the users who are not celebrities. But there also will be some tweets in a relational database from celebrities that should be included when I look at my feed. So to build my feed involves two steps. First, I check the NoSQL database to get all the tweets that have been pre-built in that feed from the unpopular users, from the small-time users, right? So that will involve one check of the NoSQL database. I also do a query to a relational database read replica to get the recent tweets from celebrities, and that does involve doing the join of data from celebrities. But because there are only a few celebrities, that database is small enough to fit on one machine. There might be a lot of users who are following, and basically every user might be following some celebrities. The way we deal with all those reads is by having read replication. So we might have hundreds of read replicas. Those all are doing maybe a lot of work in some sense, and there's the inefficiency of the scattering of the data to handle that. But that's only for getting the celebrity tweets, so it's not a huge database. The result of that that SQL query with that join is combined with the feed that I got from NoSQL to build my actual tweet. Okay, so that's the final design. And of course, like I said, the reason this works is because celebrity tweets are pretty rare. A single primary SQL database can handle all those writes, and then read replicas handle all the reads that are happening. Whereas for regular users, the tweets are going through the slower process of asynchronously updating the feeds for all the followers. Okay, so that was the lesson of today. I hope that was useful. Not really anything new here in terms of building blocks, but a review that really puts into practice the ideas of both asynchronicity and understanding the trade-offs in databases and making a pretty clever design that combines the best of both worlds. Okay, the reason that design is possible is because we understood the particular application and the fact that there were actually two different classes of users. The sort of consumers that have a lot more reads than writes. For those users, the NoSQL database works better. Celebrities are different because the traffic they generate is actually mostly reads, and they don't generate a lot of writes, but their tweets are read a lot. So we put their tweets in a SQL database. What this inequality is showing here is that the impact of a celebrity write is much greater than the impact of a celebrity read. So when a celebrity writes, it causes like lots of activity across the system because a lot of users are going to be reading that tweet, whereas the browsing that one celebrity is doing on their feed has a very, very minimal impact on the system. So actually, it makes sense to organize their data in a system that makes writes efficient and reads inefficient in a way. But for most users, it's the opposite. It's true. Okay, so the relational database is space efficient, it has fast writes but slow reads. The NoSQL database is inefficient. There's duplication of data. The writes are slow, but reads are fast. And those different trade-offs work better for different classes of users in this case. All right, that's cool. I hope you like that. I think it's a cool lesson that brings things together and relates to a real application. See you next time.